Alright, so we just finished the car truck FRQ. Did that. Oh, guys, I got a question about number 20 in your puzzle. So got a request to do this in class. So let's this real fast. You guys remember number 20 from the puzzles tutorial a few days ago? The birds of prey, flying, boa. Okay. And I have the solution right now, so I'll just show you the solution. Okay. So there's a birds of prey question. It starts at 1,200 meters up. It can dive at 1G, and it says how fast it's going to crash, basically. And then if it's allowed to go up to like 6 Gs of acceleration, maybe it's got like some bone structure that can handle like 6 Gs. Okay. Then what would the necessary stopping distance be from that speed? Like that. Okay. So here, I wrote the solution here to show you guys. Again, got a request to see this. So here's the you see this bird here. Say it got a little mouse down here. He said, okay, he's 1,200 meters up. He sees that mouse go. You're gonna dive on the mouse. Have you ever seen one of these birds like dive? Like, dive so fast. Okay, so suppose he dove the whole way. What would his speed be? Okay. So I made a little taxi V table. I know the height he starts from in meters. I know Earth gravity. I mean, that's what's allowing him to dive, right? Earth gravity. Okay. Let's say he starts from rest. Okay. Would that be the third kinematic equation right here? Yes. Third one. Right. And then, okay, you can plug in what you know, starting from rest. Okay. Guys, here's the answer in terms of variables. The crash speed always ends up being square root 2gh. Actually, that funny looking expression does show up all over the place in this class. This will not be the last time you see this. So crash speed should be square root 2gh. Okay. If AP asks this, then make sure you derive this from scratch. Start with the third kinematic formula. But I mean, if you see that, then that means you're on the right track. Okay? So you plug in the values, you get 153 meters per second. Is I compare that to the measured values of 157 meters per second. Yeah, it's pretty close, right? Or if you use 10 meters per second squared, maybe you got 155 meters per second. Okay, so either of those would be okay. Then the follow-up question B said, well, suppose the bird's allowed to go up to 6G. What if he spreads his wings out, like somewhere around here, and he's like, and then like slows down to come to a stop, basically. Right? Then could he like sort of decelerate and slow down to come to a stop? Okay. And let's say he's allowed to accelerate up to 6G. Okay, 6G. How many meters per second squared would that be? 6%. Yeah, about 60. Right? Because every 1G is 10 meters per second squared. Right? Now, so you could either use 58.8 or 60. Either one's fine. Right? Meters per second squared. Starting from, well, yeah, pick your favorite initial loss. Okay. How much time and how much distance would that take? Okay. So pick the second kinematic formula to solve for time. I got 2.6 seconds, like that. Boom, boom. Okay. If you wanted to know how much distance would that be, I can go back to the third kinematic formula. Say he has to end at 0, starting at whatever path speed he's going. Right? How much distance would that take? And I got almost 200 meters. Right? And in context, if he dives from 1,200 meters, well, okay, no. I guess if he was driving that entire distance, he would need an additional 200 meters to come to a stop at 6 Gs. Okay. All right, so I want to hit that one. If you need more time to look at that, you guys know I'm going to post this video. You can pause the video and get a better look at that. Okay. My honors class yesterday, we did do a Kahoot on linear motion questions. I think it turned out pretty good. I did post that video to Google Classroom, so if you want something extra to do, probably about 20 minutes long or something. All right, so let's. Okay, let's do this. Let's move on to projectile motion. I might get you guys started on projectiles today, but ideally, yeah. Okay, ideally, if I can, I do want to have you guys do this reaction time lab before the end of class. So I'll see if I can fit both parts in here. Okay. There's right. You guys know you have an AP classroom open that I want you to have finished by the time you come to class Monday, so we can go over the answers then. Right. All right. So. Let's do this. We're gonna take all this kinematic motion into 2 dimensions. You guys ready for 2 dimensions? Yeah. All right. So actually, here I'll show you guys a video first. I think that'll be a good way to do this. All right. Let's do this animation. All right. Now, for this 2-dimensional motion, it's the exact same kinematic formulas. You just have to consider what's going on vertically versus what's going on horizontally. So this cannon is going to blast this cannonball at an angle. Ooh, at an angle. Okay. Now, do you remember doing vector components in this class? Like v sub x, v sub y? Ooh, look at that. So there's the full blast speed is that orange velocity vector. Okay. But now we're going to break this apart and say, well, how fast is it going across the field? That's this red v sub x. And how fast is it going strictly up? That's this green v sub y. You see that? In fact, if you take that green vector component and slide it over, does this make a nice right triangle right here? Nice right triangle? Look good, right? Right? And okay, you got like a blast angle right here. You guys see all that? All right. Now let's see what happens to the motion of this cannonball as it goes through the air. Let's see. Let's check this out. I might play this a few times, right? Guys, what basic shape do you think that cannonball is tracing as it flies through the air? It is a parabola, isn't it? Yeah, that's a parabola. That's a parabola, right? Now let's focus on those components. Guys, just focus on this red component, this v sub x. What's this v sub x doing? Staying the same, right? And why would it ever change? If we're ignoring air drag, which we're still ignoring air drag in this class, right? Then there's nothing to sort of slow down horizontally, right? Guys, which way does gravity pull? Gravity only pulls which way? Straight down, right? So yeah, if you were way up in a blimp, like way above, watch this thing, it would look like it's going pretty much constant speed across the field. You know, if you're just picking up its horizontal components. Do you guys see that constant speed across the field? Right? Is that okay? Right. Now let's look at the green component. You guys see this v sub y? Right. Now, is gravity pulling on that vertically? Yeah, gravity's pulling vertically. Right. What rate do you think that green vector is changing? 10 meters per second per second? Yeah, it's that color. 10 meters per second squared, isn't it? 10 meters per second per passing second. Yeah, sure is. Right. All right, so really kind of nothing new, right? It's just the same thing we've been doing all along. Right? You just have to consider what's going on vertically and what's going on horizontally. Right? Combine that with the vector components, like the sine and cosine that we did a few weeks ago. That was well, one reason with the setup for all this, right? Yeah, now you got a projectile. Right, so switch over here, let's put this together. Yeah. So you got the big old field right here.
Okay, you're not gonna do very much.
Let's have a little tiny cannon. Right, so this is projectiles. Projectiles. Okay. Go ahead and let's aim the cannon up at, let's say, 37 degrees above the horizontal. Right, so like so let's have a V blast of 50 meters per second. Let's have this at 37 degrees above the horizontal. Okay? Yeah.
Are we drawing this on?
Okay. No, this is just for your notes. Yeah. Guys, this is for your notes. That half page is going to be for the lab later. Yeah.
Good thing I wasn't using it.
Come on, get that.
Yeah, for sure.
Okay. Now, you guys imagine it's probably makes a, you guys said that's a parabola shape, right? Parabola? Okay. Let's split this into maybe 6 seconds of flight. So go after 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Right. Right. Well, I know it's going to be 6 seconds. I'm kind of giving away. Like, how would I know? It takes 6 seconds. You'll see once the numbers play out. Right. Now, first thing you have to do at the point of the blast is break this into components. Say, well, how fast is it going across the page, and how fast is it going strictly upward? Right. So with that. All right. Guys, what is this component equal to? I'll call it v sub x. It's equal to what times what? Yeah, 50 meters per second times sine or cosine. It's adjacent to the angle. That makes it a cosine of 37 degrees. Okay. In fact, why did I pick 37 degrees? That should look familiar. I'm setting up what triangle geometry? 3, 4, 5?
Oh.
Guys, is that 3, 4, 5 triangle? It's got a 37-degree angle in it. Look for that on the AP exam also. Okay. So here, maybe you put this in a calculator. What are you guys getting?
Oh, I should do that.
40 meters per second. Okay. And then this component right here, would that be 50 meters per second times what? Being the 37 degrees? That comes out to what? 30 meters per second. Because you can put it in your calculator. Those won't be exact numbers because 37 degrees is rounded a little bit. It's like 30, I think it's like 36 point 87 something degrees. Whatever. Right? Here. Okay. Okay. I'll do it here. So if I take 50 meters per second, you guys got calculation at desk. Okay. I do cosine of 37 degrees. It says 39.93. Okay, let's call it 40 meters per second. If I scroll up, scroll over where the cosine is, I put in sine, right, to get this leg right here. It says 30.09. Okay, let's call it 30. 30 meters per second. Right? Okay. Now, 1 second later, it's flying kind of at this angle. And then 1 second later, it's flying kind of like this, right? And then 1 second later, if it's going, well, we'll see what happens. Okay? See if I break this into components. Guys, notice I'm dashing the components. See, I'm going dash, 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 dash. You see that? Dash, 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 dash. Don't make your components solid because then you're like double counting them. So make sure you're dashing your components. Okay. Now, guys, is this Vx 40 meters per second? Is this still 40 meters per second going across the field? Yeah, this is still Vx is 40 meters per second. This is still Vx is 40 meters per second. This is Vx is 40 meters per second. Yeah, it's going 40 meters per second across the field all the time. Right? There's no air to slow down. Gravity's not pulling horizontally. Gravity's pulling vertically. You guys see that? Right. Now, if it was going 30 meters per second strictly upward, kind of like, ooh, if you threw a ball straight up at 30 meters per second, would it have the exact same vertical motion as this cannonball? Like vertically? I think so. Like how fast is it going 1 second later, strictly upward? 20 meters per second. There's your Vy. Okay. 1 second later, how fast is it going strictly upward?
10.
Yeah, 10 meters per second upward. 1 second later, how fast is it going strictly upward? 0. Okay, that's how I knew it was going to peak it after 3 seconds. Well, I mean, I sort of had this pre-ready to go, right? Okay. It's going 30 meters per second, 20, 10, 0. And at 0 meters per second in the vertical direction, so at this point, V sub y is 0 meters per second, then you know it's hit a peak, right? Is that true? Right. And then, what about, it's going exactly horizontally, just at that one instant? Yeah, just for that one instant, it's moving strictly horizontally. Right? And then it kind of comes down. All right, and now its angle is always changing. Always changing, always changing. Changing angle. Okay? But if you split these into components, put little arrowheads on these components. Okay? Is this going to be 40 meters per second across, 40 meters per second across, 40 meters per second across? Like that? Okay. And what about down? Is this going 10 meters per second down, 20 meters per second down, 30 meters per second down? Is it? In fact, if I'd say, what's the total crash speed? Like how fast is it crashing into the ground? If you point a radar gun at it right there, bam, what's the radar gun going to read?
25. 44. Wait, right when it hits the ground?
It's about to hit the ground. It's like a millimeter above the ground. Somebody points a radar gun at it. How fast?
Pretty fast.
Is it going across the field at 40 meters per second?
Yeah.
Is it coming down at 30 meters per second at the same time?
70. Yeah. A really smart number.
A really smart number? You getting closer?
10. I'm getting closer, guys.
Guys, this is what shape is this? A right triangle. It sounds like a job.
50. It's
Pythagorean! It's 50 meters per second. Oh, yeah, you said 50 meters per second. All right. You got 2 liters. Yeah, 50 meters per second. There you go. That's it. Yeah. Do you guys also see by symmetry? The cannonball blasted it at 50 meters per second to start with. Now it's sort of slowing down on the way up. It's sort of speeding up on the way down overall. But yeah, it ends at the same crash speed for the same elevation, right? Because the cannon was also at ground level. Okay. All right. Would you guys believe that the answer was hanging behind you the whole time? Oh, it's this one right here. The whole time.
No way.
How about guys? Next week, or in a few days, one of the labs will have you guys do. We're gonna take a launcher out to the balcony out here. We're gonna launch some bouncy balls, little bouncy balls. right? And if you aim it straight horizontally, it's gonna. Ooh, what shape is this again? Yeah, parabola. Yeah, parabola. Right. It's gonna land somewhere out there. Right. Let's work around this. Let's change some variables. What if there was no gravity and you launch this horizontally? If there's no gravity, what does it do?
It's gone.
Yeah, just keep going, keep going, keep going. Right, just keep going in a straight line. Right. What if there's maximum gravity? What if there's
Go down.
yeah, go like this. Huh. So do you think the exact location where it lands has something to do with the gravity field?
Yes.
Yeah. Okay. Wait. Does it also have something to do with this height right here?
Oh wait.
Huh. Okay. So, how high this ledge is? I think the taller the ledge, the more time it has to be in the air for, right?
Yeah.
Right. And the stronger the gravity is, the less time it would have to be in the air, right? Meanwhile, it's going across the field the whole time. You guys see we're juggling two dimensions here, like how far across and how far down in a gravity field, right? Right. So here's kind of the short of it, or what's kind of the up, right? How far it falls down, I can call this y or h, right? I could call it 1/2 gt squared, where t is the amount of time it's falling for, right? Suppose you know what y is, right? Could you guys take some meter sticks and measure y? Measure that height right there?
Yeah.
Okay. And then let's say you're allowed to know g. Okay, you're allowed to know g. Pick your favorite, either 10 meters per second squared. I'll probably just do that. 9.8 meters per second. Could you solve for the amount of time that it's in the air for? Right. Actually, would that be a more accurate way? What do you think would be more accurate? Like calculating t by using this red equation, or sitting here with a stopwatch being like, what do you think's more accurate? How about the equation? Yeah. You guys go from your card incline lab trying to start and stop it exactly. Ooh, that's really hard. Right. Unless maybe you took a video and did slow-mo, but that would be illegal. So once you have that time, could you go down here and say like, I took a meter stick or a trundle wheel and measured so many meters out there, point, lands right there. Could you take your calculated time here and your blast distance here and calculate the blast speed? Okay. All right. You guys see in principle you could do that? Okay. That's the question I'm gonna throw at you guys here. Okay. So I got this sort of pre-solved. I don't know if I should show this to you guys, but there. Well, I've got two versions. Okay. So you have to juggle what's going on vertically, what's going on horizontally. Okay. Everything vertical I put in red ink over here. Everything horizontal I put in green ink over here. Okay, see red for vertical and green for horizontal. Okay. Okay. But time is guys, what is time? A scalar or a vector? A scalar, right? Like displacement, height, that would be a vector that could only be vertical or only horizontal, right? Gravity field's pulling vertically, right? But time, well, that's a scalar. It doesn't really have a spatial direction to it. Okay? So the time is the same either way. It takes the same time to go from here to here, whether you analyze it vertically or horizontally. Okay, so you can substitute that time. You can calculate the blast distance. Okay? If you did know the blast speed cannon, like I know this cannon can blast 100 meters per second. I know. If you did know that, then you could predict exactly where the ball is going to land. And that's what this is. A little bit different. Right. Something like that. Right. Okay. Well, okay. That one's fun too, but I might say this one for a different day. Okay. All right. So, let's do this. I put this on your desk, so you guys have this. Okay. Let's look at the categories of questions and sort of how to think about these. I think I'm going to take tomorrow to solve as many of these as I can with you guys. Okay. So, and I was looking at your textbook too, because my original plan was to draw questions out of your textbook, but I like my questions better, so we're going to do this. By the way, side note, AP does not ask a whole lot of projectile questions. You might see like a couple of them. Okay. Right. Look at that. So the questions on the left side are all the same category. They all involve a cannonball blasting horizontally off the edge of a cliff. So basically, this picture right here. So the left three questions are all scenarios that look exactly like this picture. Okay. But I give you different kinds of information. You guys see I have like a double table? Okay. The left side, guys, left side, where there's only maybe 3 kinematic variables to juggle. Would that refer to horizontal or vertical information? Horizontal. Guys, horizontal. And this one over here, I'll call it vertical. Okay. In fact, the kinematic formulas, here's these 3 kinematic formulas. When you're working with projectiles, horizontally, there's only one that even matters. Right? Because, guys, is there acceleration horizontally? No, gravity's not flowing horizontally. Okay? So, guys, if this A is 0 right here, oh, great, the speed's the same everywhere. Okay, that's nice to know, I guess, but it doesn't really solve anything. Okay, how about what if this A is 0? Oh, speed squared, speed squared. Okay, well, it kind of tells me the same thing. Okay. But this top one, what if this A is 0? Do you guys get distance equals speed times time? That's all you're ever working with horizontally with projectiles. That's it. That's the only equation. X equals vt. Right? This would be v sub x. Okay, so this is strictly in the horizontal direction. Okay. Okay. So like in your notes, this would refer to like the 40 meters per second where it's going horizontally, 40 meters per second across the page. Okay, that would do it. Okay. X equals vt. Okay. Now vertically, you have the full story. Vertically, you're working with all these. It depends on what information you have. So every one of these scenarios, I gave you different kinds of information. In fact, look at this one down at the bottom left. See where it says the cannon fires a cannonball horizontally off the edge of a cliff. Okay, sorry. On an alien planet, alien planet. Guess what? You don't know right away. The gravity field. But I give you enough other information. Like I tell you the blast speed, I tell you the how far it lands away, I tell you the height of the cliff. There's enough information there where, in principle, you can solve for the gravity field. Can I get that? Okay. Now the 3 questions on the right look more like actually more like the one we just did in the notes, where you're on a big old field, big old plane, and you aim the cannon up at some angle and launch it that way. Okay. Okay. And then mathematically, it's very similar. Right? There's a horizontal side, there's a vertical side. I give you enough information. Okay. And guys, what variable? What's the only variable you're allowed to transfer from vertical to horizontal, or vice versa? Time. Right? Because time's a scalar, so time's allowed to go both ways. Because once you solve time, you can time's the same, no matter which way you analyze it, vertically or horizontally. Okay, guys, good. Okay. Now on the back side of this page, there's some more scenarios. It's like a hybrid combination. So yes, we have the cannon on the cliff, but also it's ramped up at some angle. Now you got both of them. So this one on the left, I was walking you guys through like step by step by step, and I gave you a little multiple choice to make sure you're on the right track. Okay. And then the ones on the right are a bit more open-ended. Great. So like I said, my plan for tomorrow is to then all day tomorrow do as many of these as I can with you guys. Okay. But there's still, we got just enough time to do this one last thing I want to do in class. Okay. And actually, it's going to be one of the building blocks to your lab next week. You guys remember next week you're going to take the launchers out and figure out what's the blast speed and go over all the strategies for it. Okay. So, guys, the lab you do today is going to help you next week also. Okay? It's time to figure out your reaction time. So, you guys got that half page? You guys got a half page? Okay. So, write your name. Okay. They'll turn us in by the end of class. Call us reaction time lab. Okay. And then let's make this table. Okay, so it's something like this. So we'll have different trials and units. Okay. So you have like trial A, trial B, trial C, or trial 1, 2, 3. You do it. Right? How far does the roller fall? And what's the time? Okay. Now, guys, if you're trying to solve for your reaction time, are you using the stopwatch today? Yes or no? No. Because it's sort of like trying to figure out the very error of starting and stopping. It would be, I don't know how you do that. Okay. Guys, what is sort of your stopwatch today? Yes, this right here. So what if you're holding get that back. What if you're holding the roller like this and your friend has their fingers at the 0 centimeter mark? Okay, so you want your fingers at the 15 mark? You want to start at the 0. Let's start at the 0, right? And then you drop the roller, your friend catches it as fast as they can. Whatever marker your friend catches the roller at, that tells you how far the roller has fallen. In this case, maybe like 16 centimeters. Right? Do you guys think you can calculate, here, if you measure how far the roller fell, just by seeing where you grab it, basically. Okay. Can you calculate how much time it's been falling for, and therefore your reaction time? Okay. So guys, by the end of class, turn in this page and also turn in your FRQ. Okay? And I will put both of those in the grade book.